Okay, thank you everyone for coming. Let me introduce Harry, who is visiting us from Manchester. Harry did his undergrad at Bristol, and then moved to the University of Exeter for PhD. And I guess after that, since then, Manchester, now as an more or less independent researcher under the Royal Society Fellowship. In terms of research, I encourage you to check his webpage, Google Scholar. Quite interesting combinations, starting from classical questions on stochastic thermodynamics, noise, as you can see, and moving on to quantum thermodynamics, and then questions of measurements. And so, yeah, as you can see, it's general noisy quantum systems. And yeah, please.
Thanks. Yeah, thank you. Yeah, thank you everyone for coming. Yeah, so my talk is going to sort of be a combination of talking about open quantum systems theory and quantum thermodynamics. So our group in Manchester, they sort of specialize in sort of modeling open quantum systems where you go beyond sort of traditional assumptions, in particular, going beyond the assumption that the environment that your system is in contact with is weakly coupled. So we're very interested in looking at strong coupling regimes. So for myself, I specifically more look at quantum thermodynamics. So this is really concerned with how irreversibility and heat and work and things like this can be sort of represented in microscopic quantum regimes. So yeah, one of the things we realized is that a lot of the things in quantum thermodynamics that you might be interested in, like in particular work statistics. So I'll be explaining what this is in detail. A lot of the studies in work statistics really are sort of phrased in terms of weak coupling assumptions. So we were very interested in seeing what do work statistics look like in these more extreme strong coupling regimes. So yeah, this work was done with Owen Dieber, Asan Nazir, and Jake Gillis-Smith. So these all at Manchester. I think most credit for this work needs to go to Owen because he did the bulk of this work in his PhD. So yeah, so I'm going to start by telling you what I mean by work, right? That's the most important thing to start with. Work being the sort of useful energy that you can get out of the system. So I'll define how you define like not just work, but it's statistics. This is the important thing because it's a small system, so it has a lot of fluctuations. So yeah, so then I'll tell you about the standard way in which people model work statistics in open systems. And the focus of the talk will be looking at how do we go beyond these standard assumptions where you have strong correlations, strong interactions between your system of interest and its environment. So the results we found is that we can use some open systems theory techniques to look at interesting new things that you can see in the work statistics from the effects of the coupling. So yeah, I'll be focusing on the Landau-Zener protocol and the work you get out of that as the kind of main example of this. Sorry, this is a bit slow. Yeah, so just to motivate everything. So when you have a small system and you're interested in thermodynamics, you need to worry about fluctuations because, you know, things like heat and work and the way you can exchange energy is going to be really influenced by both thermal fluctuations, but also quantum fluctuations. So when we talk about work, we actually need to consider things like the work distribution, like how is the energy changes distributed in time. So this field covers both classical and quantum regimes. One of the key things is that there are certain laws which constrain the work distributions in these regimes known as fluctuation theorems. So this here is called the Jarzynski equality. and it really places a restriction on the types of work distributions you can observe in nature. But one of the key questions is, how do environmental effects affect the work distribution? So this is something we wanted to look at, particularly when the interactions are really strong. So this is just the kind of general setup that we're considering here. So we have a system that's immersed in some environment at some temperature, and it has some internal Hamiltonian that we change in time. So it goes from some 0 to tau value, and changing the Hamiltonian is going to cost work. So there'll be some mechanical energy that has to either be put in or is taken out, depending on how you change the Hamiltonian. So just from kind of a microscopic description, we would imagine that this is a whole unitary process. So you have some, say you're initially in equilibrium, but you drive this Hamiltonian in finite time, you're going to be kicked out of equilibrium. So you have some final global state, which is not going to be equal to its thermal state. So because it is kicked out of equilibrium, you have some dissipation. So I refer to this as dissipated work, which would be the difference between the work done during this unitary and the equilibrium change in free energy. So if you're interested in just the second law of thermodynamics, this is a positive quantity on average. So dissipation is positive. But generally, this work W is a random variable. So this statement only holds on average, but really you can have fluctuations in this. So we're more interested in the distribution of this value rather than just its average behavior. So there's a number of reasons why you'd be interested in work statistics. One of the reasons is of course, if you're wanting to control the system in some reliable kind of way, you need to make sure fluctuations are kept small, because you don't want to just minimize dissipation. That might save you energy or whatever you want to, however you want to phrase it. It's no good if you have really high fluctuations. So this is why it's important to consider the higher order behavior. One of the other things people use this for is to study free energy profiles of sort of complex systems. So if you monitor work, you can kind of extract information about the free energy landscapes of processes. Other kind of non-equilibrium behavior, like Hibble-Zurich scaling, out of time ordered correlations and things like this. All of this stuff you can access via measuring the work. And then finally, just another thing is to identify distinctly quantum features in the work distribution. So, a question in quantum thermodynamics is always, what is actually quantum in the behavior? So you can use the work distribution to really pinpoint quantum effects. So there's a whole range of reasons why you would want to look at these distributions. So the way that this is all defined, I'll take you through it. So remember, we have some system in red here in contact with an environment. It's driven out of equilibrium with some unitary. Now the unitary arises from some time-dependent process. So we divide the Hamiltonian into various terms. So we have some internal Hamiltonian for the system. That is the only thing that we're changing in time. So we only have local control. We have some environmental Hamiltonian, some kind of bosonic reservoir, for example. We have some interaction as well between them. So standard approaches would assume that this interaction is very weak, but what we're going to do is go beyond that and assume that it actually can be much larger. But the way you would define the work across this process, to do that, you actually have to measure the system. That's the key thing. So at the beginning, we measure the global energy. So we'll get some energy eigenstate that the system is in at the beginning. Then once that evolves, we need to look again at what the energy is at the end of the process. So we'll see some final energy at the end. The work would then be the difference in those energy eigenvalues. So this is usually referred to as the two-point measurement approach to defining work. Let's go to the next slide. No way, it's not working. Okay. Yeah, so just to get straight into the more technical things already, what we're normally interested in, rather than the work distribution, is its Fourier transform, because it's much easier to work with. So this contains all the same information about the distribution here. It's just a better way of representing it for theoretical purposes. So if you have this characteristic function, you can get all of the moments of work just from taking derivatives of it. So the way to actually calculate this is, so remember this thing is formed by doing projective measurements of the energy at the beginning and end. So it's not just it's not an observable, it's essentially a two-time correlated function. But the general method is to write it in terms of, I would call this, say, it's not really a density operator. It's an operator which depends on this counting variable, this chi here. So the main thing you can do here, so this will depend on the full dynamics of the bath and the system. So it's generally we need to make some approximations on this because we can't work with the whole system. So what we do is okay, I can already spot an error here. So, oh no, sorry, this is fine. So yeah, you want to try and write down an operator which captures the work distributions. But remember, because we're only applying time dependence on the system, we can trace out the bath variables and try and get some approximation for this reduced state. It's very similar to how you would just want to, if you were just interested in the actual density operator, you would do this. We can actually do this for the full work distribution. So that's the general idea. And then depending on what approximations you make here will govern what your predictions are. Yeah, so what we realized is that there's not many results in the literature about what happens if you assume that this interaction is pretty strong. So, you know, I think it's an important question, is how do we model work distributions when we have these strong couplings? The problem is it's obviously a formidable task, right? Because you can there's very few systems you can treat exactly or even very well if you don't make some approximations on this, because the work distribution depends on the full spectrum of the global Hamiltonian, which you don't really have access to. The approach we decided to take was something called a polaron transformation. So I'll tell you about how that works. But it's really a trick in which we can map the system into something that's a bit more manageable, that still allows us to treat this coupling as non-perturbatively, essentially. So yeah, so I don't know how familiar you are with particular systems where strong coupling is important, but I guess a couple of examples would be semiconducting nanostructures, where you have some two-level system or more that's sort of coupled to lattice vibrations or phonons, which can be actually significantly stronger because the system is so small. It's not necessarily very accurate to assume that these couplings are weak. So yeah, I mean, there's a lot of literature now looking at systems where weak coupling theory breaks down. So it is a experimentally relevant regime nowadays. Okay, so this is describing the sort of weak coupling approach that you might take to modeling the dynamics. So this is what I would say is insufficient for what we want to do. So normally you would try and derive like a Markovian master equation for the reduced state of the system. So remember, we're driving the system Hamiltonian in time. If we look at the reduced density operator, as long as you assume this coupling is weak, or rather make the what's called the Born-Markov approximation, followed by other approximations, you can derive what we would call an adiabatic master equation. So if you just look at the structure here, we've got the unitary part here related to the system Hamiltonian. Usually you have to include some Lambshift term, and you have a dissipative term at the end here, which this is your Lindblad causing like the non-unitary parts of the evolution due to the interaction with the environment. And this framework is sort of the nicest way you could do it, because these jump operators here, they change instantaneously with the energy eigenstates of the Hamiltonian. So this requires a lot of approximations that are probably too ideal. In particular, you have to assume that this is changing quite slowly. Again, as I mentioned, this has to be really weak. And the main thing about this adiabatic master equation is it tries to always bring the system back to an instantaneous thermal state at each point in time. So you can use this to calculate the work distribution as well. As I mentioned, when you calculate the work distribution, you have a similar operator that contains all this information, which is then you trace out the environment and you make the same approximations you make here, and you'll get some master equation that tells you how to calculate the work distribution in this way. So this is the weak coupling approach. So yeah, we were interested in going beyond this kind of approximation. So the key question here is, in any kind of solid state device, quantum dots coupled to phonons, what kind of impact can the phonons have on the work distribution? So this kind of system, you can manipulate it with some laser adiabatically. This is like the time dependence on its Hamiltonian. So it's a two-level system here with some frequency splitting. The reservoir or the phonons essentially modeled with like a collection of bosons. And we have just the standard interaction coupling to the Z direction and the positions of each boson. So this is a spin boson model. So you could extend all of this to higher level systems, but I'm just going to fixate on the spin case just for simplicity. Yeah, so this is I'm going to describe the polaron approach. So this is a way of treating these kind of systems beyond this weak coupling approximation. So one of the tricks that people have used is to really displace the energy structure of the system. So this S here is it's a unitary transformation which maps the system into it sort of redraws the boundary of the system. I guess this is represented pictorially here. So this kind of displacing the system in this way, it's useful because this is a unitary transformation. So any properties which actually don't depend on that are unitarily invariant can be calculated by moving to this new frame of reference. And then the key point is that when you move to this new frame, you can then treat this perturbatively in such a way that the original interaction stays strong in the original frame, but is weak once you move to this new frame. So that's the kind of general idea. So yeah, as I said, this actually allows you to maintain strong electron-phonon interactions. And so the polaron approach has been quite successful in some experiments. So it can accurately describe the effects of the environment on decoherence, more accurately at least than just the weak coupling, pure dephasing approaches. It also seems to capture sort of resonance behavior where, you know, the resonance starts depending on the properties of the environment, like the temperature. So these polaron predictions perform much better than weak coupling. So we thought this is an obvious trick we can try and use to calculate work statistics as well. Yeah, so structurally it works in this way. So remember, this is the original Hamiltonian, and this e to the s is this mapping that we're applying, this unitary. So this is you can see it's a displacement. So we're displacing the degrees of freedom relative to the various modes of the bath. So we're sort of dressing the system in this way. If we look at this transforms the Hamiltonian. So the internal system Hamiltonian now gets renormalized. So this kappa here is the renormalization constant that comes from this mapping. So it kind of changes the splitting, which now depends on like temperature and the structure of the environment. But the main thing is now when you move to this polaron frame, we can try and approximate this with the same weak coupling techniques, but in this new frame. So that's the idea. So the example we take here is a super ohmic spectral density. You can go beyond this. So our methods work for, you know, sub-ohmic and ohmic approaches as well. You just have to do something a little bit more complicated. So I'll just only stick to talking about the super ohmic case. You need to use something called variational polaron theory, but I think I'll avoid talking about that. But yeah, this renormalization term, you can see that it depends on the structure of the environment and the temperature. So this is changing the gap of the system, which makes it a little bit more complicated, but you can see why this would now start to capture some of the effects of the interaction in the system dynamics. Now, this gives you a new perturbation regime when you do this mapping. So this factor G here, we treat this perturbatively, but treating this perturbatively still allows you in the original frame to maintain strong correlation, strong coupling. Yeah, so this is just benchmarking some of the approximations that we used versus, so this tempo here is a sort of numerically exact approach that some of the people in our group use a lot. So the red line here is the weak coupling master equation, this adiabatic one. So we expect this to be less accurate than the green line, which is the polaron approach. So we're looking here at the populations of the state. And you can see here that the polaron approach matches very closely with the exact numerics, whereas the weak coupling approach, this red line, is not doing as well. So this is for a stronger coupling regime. They all kind of converge in the weak coupling regime here. So as you'd expect. So this gives us nice evidence for why our approximations seem to do quite well here. Yeah, so as I mentioned, the reason you would choose a polaron transformation is because it's unitary. So if we want to calculate things that are unitarily invariant, it's a good method. So the characteristic function, so remember this is describing our work distribution. Because you take a trace, then we can just plug in a unitary transformation here and without changing anything. So we do this, we apply our polaron transformation to the operator that tells us the work statistics. And we get this new operator here. Sorry, this should be a trace over the system. So this thing, well, rather we trace over the environment and try and approximate this in this new polaron frame. So what you can do is you can derive a master equation for this operator, which is expressed only in terms of the system degrees of freedom. So what you get is, so this is the adiabatic master equation that I showed you before, but now it's in the polaron frame. So remember, we've moved to a new frame and we've treated that perturbatively. So we can now treat the system with the really nice adiabatic Lindblad master equation. So this is why we chose to do it. So the main new thing here that you get, because remember, this is not a density operator. This is containing information about the higher order behavior. So you get this additional term here in the master equation, which is coming from the changes in the Hamiltonian over time. So the other condition that we use here is that because we can treat this new coupling in the polaron frame perturbatively, we can split the environment and the system essentially into an uncorrelated state in this new polaron frame. Yeah, so as I said, I would talk about the Landau-Zener transition. So this is where your time dependence is just a linear function of so the frequency change is just linear in time. And these are our results, basically. So this is the probability distribution or probability density of the work statistics. So this is work along the x-axis here in dimensionless units. Oh, sorry, units of the tunneling coefficient. So what we find is a comparison between the weak coupling approach, which is in the orange color, and the polaron approach, which is in blue. And we find quite a new kind of behavior here. So this sort of helped us pinpoint some new effects you get from the environment influencing the work statistics. So let me go through each of these different points. So you can see that there's a peak over here, the first peak here. This is just coming from the standard Landau-Zener transition. So this is moving you from a ground state to some excited state, because you're moving in finite time, so you can have some finite time transition there. What we find is that in the polaron approach, the likelihood of that occurring is much higher. So one of the key things is that the influence of the environment tends to make it more easy to excite the system, because you can absorb phonons from the environment. So this is going to increase the likelihood of having more dissipation, because when you excite the system, this costs work. So this is why you get this higher likelihood of this cost in work over here. So point 2. So these two peaks here, we can interpret this as absorbing a phonon from the environment. So this is another way in which you can excite the system. So again, this is another cost in work. But again, so these peaks are shifted because remember, we're renormalizing the gap of the system as well because of the environment. So the cost in work is going to be different between the two, from the weak coupling and the polaron approach. Point 3, so this is close to zero cost. So this is where you excite the system from a non-adiabatic transition, and then you emit another phonon, which brings you back down to the lower level. So this kind of process generally has quite a small cost. This peak over here is like the reverse kind of process of this. So you go the other way around. So again, the weak coupling approach predicts these events to be much more likely. But as I said, the polaron approach tends to suppress this kind of process. So this is why it's much less likely to occur. Yeah, and so another interesting thing here is you get actually another type of transition which you just don't observe in the weak coupling regime. So this is a 0.4 here. So this is where you can excite the system, emit a phonon, and then excite it again. So I think because again, the environment is increasing the chance of being able to be excited like this. This kind of process you don't tend to observe in the weak coupling regime. So yeah, this highlighted to us that the strong coupling can have a lot of noticeable effects on the work distribution. So I think it highlights that it is important to consider environmental effects, because you would miss all of this kind of behavior if you just treated it with the weak coupling approach. Yeah, so again, this renormalization of the system is going to shift the peaks in such a way that you would miss if you just had weak coupling. So yeah, what you find with the weak coupling, the positions of the peaks are not going to depend on the coupling, because again, you're throwing away this influence of the environment. Whereas the polar theory actually correctly captures these shifts in the work costs at different values. Yeah, so another thing we observe is that generally the coupling tends to both increase the dissipation, but also the fluctuations. So I would say it's a detrimental effect coming from the coupling, which I think is to be expected. So this is the coupling strength is along the x-axis here. So this is just the average work. And let me think. So the dashed lines are the weak coupling regime, whereas polar are the solid lines. So you see, as you go to the stronger coupling, your work starts to cost more relative to the weak coupling predictions. But also, I guess this was unexpected. We didn't really have a reason to expect this, but it's just what happens is that the fluctuations tend to be quite significantly more when you start including the influence of the environment. So the environment is not just adding more costs to these transitions, it's also making them more fluctuate more. So this is the other thing that we observed in the results. So if you take the weak coupling approach, you're going to underestimate both the average cost and also the fluctuations. Yeah, so the last kind of nice thing about these results is we can check that they're sort of thermodynamically consistent, which is important, because we are making approximations, and sometimes if you make these kinds of approximations, you can end up with inconsistent results. So we decided to check this, so let me just first describe what's known as a mean force Gibbs state. So this describes the equilibrium configuration of our system. So remember, our system here and our reservoir are initially in a global equilibrium state. So if we just look at the reduced equilibrium state of the system, which just comes from tracing out the environment here. So this will not be in a local Gibbs state. It will be in this mean force Gibbs state, which actually depends on the strength of the coupling and the details of the environment. So this is what we should expect to see in our system when it equilibrates. So yeah, so this is a non-Gibbsian state, because this free energy here, so it's the difference between the total free energy and the free energy of the reservoir. Because the system is correlated, this thing will depend on the interaction. So this is important for establishing this consistency, because if we go back to this fluctuation relation that I mentioned, what we would expect to see from just purely sort of exact dynamics, we would expect to see this fluctuation relation to hold. So the higher order fluctuations in work should be equal to this change in the mean force free energy. So this gives you two kind of consistency checks, because it ensures that the work done is always bounded by the free energy change. So this is the average second law, but it also prevents macroscopic violations of the second law as well. So because of this relation, this implies that the probability of the work exponentially decreases as you go to beyond the free energy change. So it becomes harder and harder to observe trajectories with work that is much less than the free energy as well. So yeah, with our polaron approach, we would hope to ensure that this holds, and it does, which is good. So yeah, so you can prove from our dynamics that the work distribution will satisfy this fluctuation relation. So this is the free energy of the polaron. So you see that it depends on this renormalized frequency here, which in turn depends on the structure of the environment. And if you apply all of the same approximations we made, you find that the polaron free energy approaches the mean force free energy in the same kind of regime. So again, we recover this result under these approximations. Yeah, okay, so I'll just summarize. So we showed how to calculate work distributions in strong coupling regimes using this polaron transformation approach. And we've showed that you get a lot of new behavior, which you don't see in the weak coupling regime. So it definitely, if you're trying to use these kind of systems to do useful things, then you know, you need to be able to capture all of the kind of higher order statistical behavior like this. So there's a lot of open questions with this work. I think the most important thing is, you know, how do you measure this experimentally? Because we're just theorists, so we've not thought of this in detail yet. Because one of the problems is that, you know, the definition of work itself comes from projectively measuring the global Hamiltonian, which you can't actually do in practice. So normally what people do when they use weak coupling approaches is they can use an ancilla to monitor the environment and monitor excitations in the environment in such a way that you can, if you record the history of that kind of process, it will approximate the work distribution in that way. The problem is, the question would be, can you do that same thing in the polaron frame? We're not sure about that yet. It would be nice if you could, because then you could actually construct these work distributions with these kind of ancilla detection schemes. So this is something we're still not sure about. Yeah, so then people in our group are also looking at other kinds of mappings and things which can go beyond this polaron regime as well. So things like reaction coordinate mappings and other also numerically exact approaches as well to get the work distribution. Yeah, so okay, I think I will end there. So yeah, thank you for listening.